Okay. Hello everyone. We'll start today's session. So this is Arun, and today I'll be handling the week four lecture, which was missed last week. I was traveling, so I could not take the last week session. So today we'll be doing the week four session, and this Friday there will be another session, same time 6 to 8. In that we'll be covering the contents of week five. So I'll share my screen now. Okay, in the last week we saw the different elements of visual interpretation. So we saw how the shadow, texture, and pattern plays an important role in the visual image interpretation. And then we saw what are the different types of techniques available to enhance the images for interpretation. So we saw the linear stretching, and we saw histogram equalization, and we saw what are the different types of convolution filters. Then finally, I demonstrated how to do the pan sharpening. And in this week, we'll be seeing one of the important method to reduce the dimensionality of the data, that is to decrease the data redundancy. So too much of information will lead to increase in the computational efficiencies, and it's also difficult to analyze the data. So we try to make some analysis so that the dimensionality is reduced, that is principal component analysis. Then there is a small technique by which you can visualize the different bands in QGIS. So we can plot the two bands into x and y axis. That's called as a feature space plot, and we'll be able to see how the two bands are either correlated or non-correlated, and we'll be able to decipher some things out of that. Then we'll see the spectral enhancement. That is, we have the band ratio and different indices. Uh, Here we'll be seeing some of the indices which are helpful in identifying the vegetation, the water body, and the urban land use classes. And later we'll move on to some of the basics of image classification. So there are two types of classification: supervised and the unsupervised classification. And finally we'll be seeing the accuracy assessment, how to calculate the accuracy of the classified image. So first topic is the principal component analysis. So here, principal component analysis, we try to reduce the dimensionality of the data. So how do we do that? We will be shifting our axis. This is the x and y axis, band 1 and band 2. So we will virtually shift these axes to the highlighted blue line, which is the principal component axis. So the center of the axis is the mean of band 1, and the center of and the other point is the mean of band 2. And we are rotating the actual axis to by some degree, so that it will capture the maximum variability in the data. So the essence of PCA is that we project the higher dimensional data to a new coordinate system, that is the PC1 axis and the PC2 axis, to reduce the data redundancy. Here when we do that, there is some loss of information, but we should reduce the dimensions such that it is able to capture the maximum variability in the data. and we will be able to get maximum information out of it. And when we do the analysis, we will get a number of principal components. So maybe let's say 5 or 6 components. And out of the 6 components, we will be choosing only few components. Let's say 3 components. And if you uh, sum up the variance of these 3 principal components, you will be able to capture high variance of the data. Only like 1% or 2% will be left over. And one more thing to remember is that the principal axes are orthogonal to each other. So this is what I was saying. So in remote sensing, when we see there are n bands, and we need to reduce to m number of principal components, and m is less than n. And why do we do that? Because it is economic consideration. So if you have n number of bands, it will be computationally intensive to analyze the data. So we make use of the principal component analysis to reduce the dimension. So here when we this is one of the sample data. This shows the output. So here the number of principal components are 7 components, and if you see the last column, the cumulative column, it indicates the variance in the data. So the first principal component will be able to capture 84.68 of percentage of variance. Then second component 10%. So if you sum up, it is coming to 95.67%. Then the third component is capturing 3.15 percentage of the variance. And when we cumulate it, it's about a 98.82%, and so on it goes. So if we plot the explained variance, that is your cumulative variance, that is your percentage of the variance of each principal component in y-axis, and your principal component in the x-axis, you will get this kind of a plot. It is decreasing. So from this, we will be able to see that so if you take first 3 principal components and then you cumulate it up, so it is coming around 98.82%. So only remaining around 1.18 percentage of the variance is only left out. So you can ignore that much amount of data. It's not going to cause any harm to it. And we will be able to capture 98 percentage of the variance. It will be better to analyze with this principal component. So anybody has any doubt until this point?
Yeah. So the previous slide, right, in the PCA,
Yeah.
of course, we are reducing the data and then shifting the, uh, what do you say, the axis to the virtual location and then
Yes.
rotating, right? So
Yes.
rotation, when we say, uh, logically, how it is changing the data. I mean, like, see, shifting data, I understand because we are reducing data. There is a vary in the data, so it
Yeah.
certainly shifts. I understand it. But rotation, how it is varying the data.
So when you form some clusters, initially if the data is uh, spread out in different directions, so it will be able to identify one small ellipse as a cluster, right?
Yeah,
So after you make the principal component, you are changing your axis, and this cluster will also be oriented towards the principal component. So your ellipse is actually going to rotate. So that is what the rotation is. It's just we will not be using these values for our analysis, just for our understanding. That is, we are shifting our axis.
yeah. Shifting axis is okay, but that's the rotation only. I was just confused.
Yeah,
That's
it is
all.
the ellipse that is rotating. So your major axis and minor axis, it's going to completely rotate.
Okay.
So it is like so suppose if you have a, let's say, a cluster like this,
Right.
and another cluster like this.
Okay.
So after you make the principal component, this cluster may orient something like this, and this cluster may come something like this. So that rotation only. It's not. I hope you get this.
Yeah. That's yeah. It's a data orientation. I mean, like cluster will lose some points after shifting, right?
Yes.
Same cluster will lose some points, and it will add some more points.
Yeah,
I mean,
it will
like,
be projected onto the this blue color axis. So we are projecting the data. Cluster size is going to reduce and it's going to rotate.
okay. Yeah.
So here the steps to calculate the principal component analysis. So we should know the math before going to the software. So in software we just have to load the bands and then we just have to click run. That's the only step that will be doing. So but we need to know what is happening behind the tool. So for that, here these are the steps to calculate the principal components. So first we need to calculate the mean of the data. Then we need to calculate the covariance. Then we'll determine the eigenvalues of the covariance matrix. Then we'll find out the eigenvector. Then later on we'll be computing the principal components. So here is the example problem. So here we have feature x1 and x2, and these are example from four different bands. Let's say these are the dn values. Of course, it's just a hypothetical example. So now we'll see how to calculate the principal components. So let me just switch over. Okay. So the first step is to calculate the mean of the data set. So mean is about 8. Then so the second data set mean is around 8.5. Then we need to calculate the covariance. So if the number of data is 2 by 2, then your covariance matrix will be C11, C12, C21 and C22. Here C12 and C21 are equal. So C11 is nothing but your variance of x1, and that is given by, so your first data minus your mean, the whole square, plus second value is 8 whole square, plus third value is 13 divided by n minus 1, so that will be 3. So if we compute this, so the variance of the first data set is about 14. Next is C21, which is equal to C12. So that will be covariance of x1 and x2, that is given by 4 minus 8 multiplied by 11 minus 8.5 plus 8 minus 8 multiplied by 4 minus 8.5 7 minus 8 multiplied by 14 minus 8.5 whole divided by 3. So your C12 is equal to C21. So this is coming around minus 11. Then you have the final value. This is nothing but variance of x2. So that will be 11 minus 8.5 the whole square. So your variance of x2 is approximately 23. So now we can write our covariance matrix. It is nothing but 14 minus 11 minus 11 and 23. So now we got our covariance matrix. And the next step is to determine the eigenvalues. So to find out the eigenvalues, we will use the characteristic equation that is defined by matrix A minus lambda into I equal to 0. So your matrix A is nothing but your covariance matrix, and the lambda is your eigenvalue, and I is the identity matrix or the unitary matrix. So if we substitute, it will be 14 minus lambda, then you will have minus 11, then you will have minus 11 again, and this will be 23 minus lambda. So that will be 14 minus lambda into then if we simplify this, we will get this characteristic equation: lambda square minus 37 lambda plus 201 is equal to 0. So now we need to find out the lambda values. So we have plus or minus b square minus 4ac by 2u. So if we find out, so you can get, this will be 37 minus so you will get your lambda as 30.385 and your second lambda is 6.615. So these are your eigenvalues. So once we get our eigenvalues, we need to find out the eigenvectors. So for eigenvectors, we will multiply our characteristic equation matrix into X matrix, and that should be equal to 0. So that will be 14 minus lambda minus 11 minus 11 and 23 minus lambda. Then we just need to multiply and then form a system of linear equation. So 14 minus lambda into x1 minus 11 x2 equal to 0. This is your first equation, and minus 11 x1 plus 23 minus lambda into x2. So these are the two linear equations, and this system of equation is not independent. So if it is independent, we can directly solve by the normal method. So since it is not independent, we will solve this by a different method. So here what we will do is, we will write x1 by so x1 by minus 11 should be equal to x2 by 14 minus lambda, and we are assuming it to a value of t, and then we will find x1 in terms of t. So x1 will be equal to 11t and x2 will be equal to 14 minus lambda into t. Now we can assume some value for t, some non-zero value. So the easiest is assume t equal to 1. Now we can write the X matrix as so we are writing our eigenvalues in such a way that it satisfies the this ratio criteria. Then we will be solving by taking them by normalizing this vector. So once we get this matrix, we can use our first eigenvalue. So lambda 1 is equal to 30.385. Now we need to find out what is the magnitude of this vector. So we can find the magnitude by taking the square root of the product. I'll just write the magnitude of a vector. So we can write x1 square plus x2 square, the square root of that. That will give you the magnitude of the vector. So if I take the magnitude of that, so it will be 11 square plus 14 minus lambda square and the square root of that. So here we are writing with respect to lambda 1. So I'm putting lambda 1. Now we can substitute the value of lambda 1. 11 square plus 30.385 the whole square. So your magnitude of x1 is it is around 19.735. So once we get the magnitude, we can normalize the vector. So I hope everyone knows the normalization. So it is just you need to divide the. So since I am taking the magnitude, I should represent by double bond. So x1 by its magnitude and x2 element by its corresponding magnitude. So this is which is nothing but the first element is 11 by 19.735 and the second element is 14 minus lambda 1 divided by 19.735. So this is 0.5574 and this is minus 0.8303. So this is our first eigenvector. So similarly we can calculate by considering lambda 2. So that will give you the second eigenvector. So in this question we are just asked to find out what is the first principal component. So we will be proceeding with the first eigenvector. So once you determine your eigen value and your eigenvector, we can compute the principal component. So let's say the first principal component is given by so our normalized vector multiplied by we are this is our sample points. So x1j, that is our first sample point, minus the first mean. So we are going to shift our center to the mean. So that is what we are doing here. And second data set, we are shifting to the center. So once we center the data, so what is our X transpose? So this is the X matrix. So if I transpose it, 0.5574 minus 0.8303 multiplied by, so your first mean is 8, and your second mean is 8.5. Now what we need to do is, this is a set of data. So x11, x12, x13, x14, that is nothing but the data given in the table. So these are so this is x11, this is x12, this is x13, this is x14. Similarly, this is x21 to x24. So what we will do is, we will take each pair of data, so x11 and x21, and then we will find out what is the first principal component. That will be p11. Similarly, we need to repeat the same thing for p12, p13, and p14. So your first data set is 4, 11. So now p11 is equal to 5574 minus 0.8303 multiplied by, so this will be 4 minus 8, and this will be 11 minus 8.5. So if we solve this, we will get minus 4.3053. So this is your first value. Then your second set is 8, 4. So if we solve this, this will be 3.736. So next set is 13, 5. So your third principal component is 5.721. Then your last set. Seven come up. The P14 is minus 5.539. So we have got for the first eigenvalue, we got 4 components. Now, what does this indicate in our uh, the graph? So I will explain what does that indicate. So this is how the data looks like when we first plotted. Just a scatter plot of the feature x1 and x2, and these are the 4 points. And the center point is the mean of the first data set and mean of the second data set. Now we are going to shift the axis to this to the which is perpendicular to the points x1 bar and x2 bar. So when we draw a perpendicular axis passing through this point, so which is nothing but our principal component 1 and the principal component 2. So this is the first component axis, this is the second component axis. Did someone message? Yes, somebody has a doubt. Hello. Okay. And
will you extend that eigenvector part? That eigenvector part will you extend again?
eigenvector, yeah, I'll come to that. I'll come to that again.
Okay. Okay.
Just, yeah. So we have our axis here, and now we have our data points. So by the calculation of that PC11 and PC12, the last part of the calculation, we are just projecting our points to the first principal component axis. So this 4 comma 11, after calculation, the value was around 3 point sorry, it was around minus 4.305. So this point is the center, and towards the left we are shifting it by 4.305. So that is our first point. And similarly, we are projecting all our points to the principal component axis. And once we project that, similarly we can do the same thing for our principal component 2, that is using the lambda 2 also we can identify. So this is what is the meaning of uh, the geometrical significance of the principal component. So determine the principal components and its geometric meaning. So we are just projecting our data to the principal component axis. Okay, somebody had a doubt. I'll come to that. Yeah, hello. Okay, so here what we are doing is we are plotting the two different bands of the multispectral data, and then we are visualizing it in QGIS. So what it does is it plots the frequency of occurrence of the brightness values in the two-dimensional feature space defined by two images. So X, it plots the first band, Y it plots the second band. And by means of this, we can see how the two different bands in a multispectral data is correlated or not. And it can be further used for the regression analysis. So I have plotted example plots. So first is the red band and the green band of Landsat 8. So by just plotting this, the bright red portion indicates that there are more number of pixels which are correlated with the higher frequency. So these are all unique set of values, but the number of the frequency of that particular dn value is very high, and the blue represents the values which have the low frequency. So with this we can see how the red and the green band is correlating. It's almost if you just calculate the r square, it will be around it will be greater than zero point 0.8 for this particular plot. And on the right side I have plotted the NIR blue and the NIR band of Landsat 8. So in this you can see there is we can say that it's not very strongly correlated, but here we can see uh, the DN low DN values for band 1 and the high DN values for the NIR band is appearing to be bright. Can anyone tell me why? What could be the reason for this dark bright red spot at the top? So I will just give you the hint. You can relate this feature space plot with the spectral signature.
Entire band is mapped with the red channel. Probably that's the reason.
Uh, no, we are not mapping anything. It's just band values in x-axis and band values in y-axis directly plotted. So why is this dark spot coming at the this place? Why not somewhere else? Okay, I'll explain. If you remember the spectral signature of water, so water uh, uh, has a reflectance in the blue band when higher reflectance in the blue band when compared to the other other wavelets. And your NIR band, what happens is your DN value is close to zero. So when you make a feature space plot, when it plots the frequency of the data, so it naturally comes to a concentrate. It is concentrated at one specific area. So when you correlate it, so I think it is NIR and blue. It is not blue and NIR. It is NIR and blue. So for a higher blue band values, you have more number of NIR band in the x-axis. So band NIR value is less for water here and high for water in the blue band. So that's why this concentrated spot is appearing in this particular place. Understood? So,
No, would you explain again?
so if you remember the spectral signature, for the blue band, the reflectance of water is high when compared to any other band, correct?
Yes, yes.
And in NIR band, water absorbs and its DN value is less than that. So when you make a feature space plot of NIR versus blue, for less values of NIR, there are more number of blue values. Higher DN value of blue values are high. So that is why your dark spot is appearing here. And by this you can say that your study area is having a lot of water bodies. So and we can do by just interpreting the graph, we can make several analysis, and it is also very useful for crop phenology studies where they will make the NIR versus another band. I just forgot what is the name, what is the other band. So when they make a feature space plot, we can see whether a vegetation is growing or it is at the harvest stage, or is it healthy. Is it healthy or is it under stress conditions? All these can be interpreted by using the feature space plot. So that is the use of this. So I will just show a small demo. So by default, the plugin is not available in QJS. So we need to go to manage and install plugins. And it is not available in this also. It's not available in this list also. So we need to download the plugin and then we need to install. So I have already downloaded. So I'm just going to locate that file. So this is the zip file. I will share this file also with you. So I will just open it and then install plugin. So the plugin is installed. So if you see here, so this is the raster data plotting, that is the plugin. So once that is installed, I'm going to import some sample value, sample data. So I have imported a band 2 and band 3 of Sentinel data. So band 2 is blue and band 3 is green, and it is atmospherically corrected by using the dark object subtraction method, which I have previously explained in other lectures. So once we click on this, here the dialog box will open, and here we need to select. So what we are going to do is a scatter or density plot, and it also has the spectral profile plot and temporal profile that is explained to you in the previous tutorials. So I'm going to take a whole raster, and I'm going to plot both of it. So I will keep blue band in the x-axis and green band in the y-axis. So if we just select, it will just plot, and here we can do the curve fitting also. So maybe quadratic. So here you can see it is a very narrow plot, and you can say that band 2 and band 3 are correlated, and we need to interpret the reason for it by making use of the false color composite or some other technique. So here probably this place has a lot of agriculture land. So if I just put the Google satellite, so you can see it is agricultural rich area, and you need to compare it with the spectral signature of the plants in the blue spectrum and the green spectrum. So it will tell you the significance of the plots. So this is how you can make use of the feature space plot for visual analysis. Is it clear? Okay. So the next part is the spectral enhancement, that is the band ratio and different indices. So here we will make use of band arithmetic or band ratio and several indices to enhance the information that is represented by the dn values. So band ratio is just dividing two bands. Let's say band 2 by band 3. It is just a arithmetic value. So we will divide both the digital numbers, and then we will find out a ratio. And this ratio can highlight certain features. So let's say a classic example is your NAR band and blue band. So let's say if I divide blue band by NAR band, NAR band values are very less, and the blue band has some reflectance values in case of water. So if I just divide this, because the NAR values are very low, your water will be the highlighted image in your output. So similarly, we can make use of the spectral signature, and we can divide an absorption band and the higher reflectance band, and that particular feature will be highlighted in your output. So some of the useful ratios here I have represented. So if you do NAR by blue, your vegetation will be highlighted, and SWIR by blue, sand or rock will be highlighted. And if you remember further into the infrared region, that is your shortwave infrared, this has a longer wavelength than your near infrared. So if you divide blue by SWIR, this value is very less, and blue has a reflectance value, and this will get highlighted. So these are the band ratio. These are some of the ratios that you can use in your analysis. And when coming to the drawbacks of this, if your denominator has some zero value, zero reflectance, or it may be the no data value, your output will not be valid. So in order to avoid that, we will make use of the some constants we can add, and then we will do the ratioing. Let's say plus 0.05 and denominator also plus 0.05. That is one way of doing that. Other way is you can combine it with other bands, and then you can make some ratios. And by doing so, they have defined some standard ratios. So first one and the most important one is the normalized difference vegetation index. So that is NDVI. So it is NIR minus red by NIR plus red. And how to interpret this NDVI? So the maximum and the minimum range it can go is -1 to +1. And here the non negative values indicate the non-vegetated surface. It may be any kind of land use, water body, barren land, and built-up areas. We will not be able to differentiate that. And values close to zero represent the shrubland kind of areas where the density of the vegetation is very less, or it might be in stressed condition. And values between zero point 0.2 and zero point 0.5 indicate a healthy dense vegetation cover, and the values greater than zero point 0.6 might indicate forest. So this is the first ratio. And second ratio is normalized difference water index. So it is given by green minus NIR by green plus NIR. Again, this also varies from -1 to 1. And positive values might indicate the water bodies, and negative values will correspond to the other land use classes. So here negative values indicates dense vegetation cover, as vegetation reflects more in your NIR band and less in the green band. So when you calculate, this value will come out to be negative. And your third index is normalized difference built up index. So this is helpful in identifying the urban areas, and here it is given by SWIR minus NIR by SWIR plus NIR. So this also varies from -1 to 1, and positive values indicates the presence of highly impervious surface, and the values close to zero will have a mixed land use, and negative values could indicate other land use classes. Okay, so I will just demonstrate how to calculate this in QGIS.
So will you show previous slide again?
Previous slide, just a minute. This one. Is it this slide?
No, next one.
Yeah. Do you have some doubt in this?
A quick question.
Yeah.
See, is this NDWI, NDVI, and then ND built up, and then snow related, right? Are
Yeah.
these proven? Is it something like some research has done, and then we have been given this formula,
Yes,
and
yes,
that should
yes.
be as standard?
Yes, it is being done, and continuously research is also going on. This NDVI itself has many modifications. So you have NDVI 6, NDVI 7, and you have. I will show one more index where the moisture content will be taken into account, and they have modified the index also. So continuously research is going on in this.
Okay. So, but here green, red, NIR, and SWR we have used, but we haven't used blue in any of the like this one ratios.
Yeah, mostly because the reason is blue is scattered by the effects of atmosphere. If you remember in the first few lectures,
Okay, maybe the due to that
yeah,
low wavelength.
it has a very less surface
Wave.
reflectance value for the many of the features. So that
Okay.
is why mostly blue is being avoided in most of the indices.
Okay. So as it is the first what do you say? It the band wavelength it range is between like 0.4 to I think 0.45 it seems
0.4
right.
to yeah 0.4 to 0.5 somewhere around that.
Correct.
And your atmosphere scatters most of the blue lights, and the resulting surface reflectance is not that prominent. So if you see it will be like 30-40%, not more than that for most of the features out of the 100% reflectance.
So these formulas, right? Whatever the ratios. So these are with respect to true color composite, right? Not false color composites.
uh, no, the output of this will be a grayscale image. Then what you need to do is you need to adjust the classes, the values in such a way that you will get your resultant uh,
Okay.
output.
So
So
for as per our understanding, we may just
yeah,
match that. I mean, like
yeah.
configure that
So
channels.
based on the values, so that's why in NDVI I have indicated the range. So our output will be from -1 to 1, and we need to adjust our symbology such that these are all captured, like more than zero point 0.6, zero point 0.2 to zero point 0.5. These are some values which we will assign to visualize.
So let us suppose once we get this gray image of this resultant,
Yeah.
then we configure for the vegetation, the probably like a red band, red channel. So probably like on the resultant, right? We'll see all the vegetation as red, right?
No, here we will not be assigning channels. I will just
No,
show
not
how
here,
we.
not here.
Not
Once we
here.
get this,
Yeah,
now
we
once we
will
get the
assign.
resultant of this.
Yeah, yeah. So I will just show that now. You will understand that. So first I will compute the NDVI. So that is band 5 minus band 4. Okay. So I have imported all the required data. So I'll go to raster calculator. So band 5 minus band 4. So I should use brackets here, divided by band 5 plus band 4. So this is the expression for NDVI in Sentinel, and I will just save it as NDVI. So this is the grayscale image of your output. So the values are varying from minus 0.27 to plus 0.35. So that is the variation in this particular image. So I will assign the single band pseudo color, and here I can change my values. So let me just put quantile. Uh, okay, I'll put quantile. So what I'm going to do is Here I will use to get a range. Yeah. So here you can see. So if I select a discrete, we can adjust the values here. So value less than or equal to. So what I'm going to do, I'm going to assign all values less than or equal to 0 as red, and less than or equal to zero point 0.2. Let me reduce the classes. So 0. So this is up to 0 0.2, then up to 0. Okay, I need to keep the range in my mind. So let's say this is 0.15 and this is 0.25, and these are the values that are greater than 0.25. So I will assign some light green to this, then another light green. So you can see here, no? So now if I just remove this, you can see the agricultural area. So you will be able to find the green patches, and this is very dark. So let me zoom into that. So you can find the trees, no? These are all trees. So by adjusting this threshold, you will be able to categorize. And if I move to the light green patches, so these are all, see, you can see that spacing between the crop is different here when compared to the crops here. So these are a little bit dense than the other field. And if I go to the red spots, so this is a bridge. So you can see the bridge is coming as red. So by adjusting the threshold, you will be able to identify the different features. So another method is you can compute the histogram, and you can see here this is bimodal. So here there is a one mode, and there is another, you can say second mode is somewhere here, and you can even split this, and by means of linear stretching you can split this and see uh, like what is the feature for this particular peak and this particular area. It might represent two different types of crops. We don't know. So these are the some of the analysis that you can make. So this is
So
how
this
you,
what we have done.
yeah.
This is called FCC, right? What we have done just.
No, this is not FCC. So what I have done is I went to this file, I went to symbology. We actually used to select multi-band color. So it will have multiple bands. But what I have done is I have just selected single band pseudo color, and here I have kept it as a discrete, and I adjusted the values in such a way that I get to visualize the required range.
But this is just like similar to FCC, right? Whatever the colors we are expecting to be on the image, those we are mapping. It's just similar to
No, in
FCC.
FCC we are assigning the color to different bands. Here we are
Yeah, of
assigning,
course. Yeah,
yeah,
yeah.
here
This is
we
a
are
gray
assigning
band. Yeah.
colors to different intervals. It is not a different band. It is just a single data set. That is what.
Okay. Okay.
Yeah.
So when we wanted to study in terms of band, then we will go for SPC where we match each color to that band,
Yes.
right?
Exactly. Exactly.
Okay. See here we are trying to analyze based on the what do you say, the material, kind of material like vegetation, dense
Yeah.
forest, and then
Based on the value of NDVA, we are trying to separate different features.
okay.
So this
And the
is,
other way is the other one quick question is, see, when you are trying to this NDVI, right? You have written a formula, right?
yeah.
So basically, NDVI we normally write it as IR band minus red band, right? And divided by higher band plus red band. So, but
Yes.
you have like written the formula as band 5 minus band 4, right? So, is it
Uh,
something between?
so
Why we have to?
why I have done this is for different satellite products, your band number will change for different wavelengths. No,
Okay.
so this is Sentinel data. So I have the band information of Sentinel 2. So here you can mostly it will not vary, but for some other product, let's say if you are going for Iconos, your band 4 will be your NIR band. It will not be red band. So it depends on the product. So that is why it's always better to remember in terms of the naming than your band number.
Okay. So, but I think I have got idea of about this. Uh, like question is we got a question in the what say in the assignment, right? So
Yeah.
where they asked in terms of numerical band, they have given the formula, and then they are expecting like some sort of which ratio it would be.
Okay. Then you might have
Not
to.
ratio, indices.
So then you might have to refer the product.
Okay.
So similar information it will be available in the product website. So you need to go through that and then you need to find out.
Okay. Is it can be easily available on the like
Yeah, you
on
can just
online, right?
search. You can just search product name, band information, or band list. You will get the website
Oh,
directly.
okay. Yeah, got you.
So this is for NDVI. So now let's
And excuse me, and regarding the solutions of the assignment question,
I think that you need to contact the NPTEL coordinators because I am just additional TA for this course. There are some other TAs. So
Well,
I
basically, like once the assignment date is expired, right? So we'll be getting the
answers you will
results
get,
of the
but
yeah.
detailed solutions they will upload. I think after all the after the final week, I think they will upload. I am not
Oh,
sure of that.
no, actually, already four assignments are over. So by this time, we should get at least one solution.
Uh,
Because previously I have also attended some other courses. So at certain interval, they are sending the solutions.
okay, then maybe I need to find out from the other people. I'm not aware of that information. Yeah. Okay. So the next ratio is NDWI. So that will be so your NDWI is green minus NAR by green plus NAR. So that will be B3 minus B5. So B3 minus B5 divided by B3 plus B5. I'm saving the output NDWI. So again you got the output. So here the range varies from minus 0.46 to plus 0.16. So this place on the date of this image, I think the amount of water content in this particular area is very less. It is only 0.16. So again I will go to single band pseudo color, discrete. I will give quantile. I will have, let's say, three classes. Only very less values are there. So value less than minus 0.3. So let that be my first class. Four classes. Minus 0.25 is the first class, then 0 is the second class, then 0.08 is my third class, and greater than 0.08 that I have indicated. So let this be red. Now you can see, right? So if I just oh, dark blue greater than 0.08. Okay, there are very less values. Okay, so I have just changed my threshold a little bit. So here you can see some of the features are highlighted, and if I go here, so it's a lake, and your river is also there. So here the water is flowing, and the rest of the bed is dry. So that has come in red color. So this highlights your water body, and if the soil is also very moist, that also will be indicated. I think it's a well irrigated area, so it is appearing as a blue color pixel. So that thresholding needs to be done. So when you go to the histogram, so based on the histogram, you need to set your class. So this values which I adjusted, based on your histogram, you need to adjust that. So you will get a better classification output. So similarly, we can calculate the NDBI. So your NDBI is SWIR minus NIR. So SWIR is band 9, NIR is band 5. So band 9 minus band 5 divided by band 9 plus band 5. This is NDVI. So if you see here, the value is not positive at all. So there is very less urban area. So by this itself, you can understand, like this is a rural area, and here is the mixed land use. So let's see what the histogram tells us. So it is more or less uniform. So here also I'll have 4 classes. So the maximum value is a point minus 0.65. So I'll keep my threshold as less than minus 0.45, and this one I'll keep it as minus 0.3, and I think I need one more class, minus 0.45, minus 0.3, minus 0.10.
So are you taking these values randomly or there is any basis?
So I am just making it like approximately. You need to study the histogram in detail, then only you can assign this value. Okay. So I'll keep this as red, then So even this threshold is not proper. Okay. So if you see here, so you are getting mostly negative values because this place has lot of barren land. So these are all barren lands, and there you are getting dark red. And this is not an ideal place to calculate NDVI, but anyway. So if I go to the settlement parts, your value is still negative, uh, but there are some patches which have a higher NDBI. So this area is not ideal for calculating NDBI. So it's a purely rural area. So your results will be not proper. So just to give an idea, like this is how we will calculate the NDBI. So here there are some patches. So one of the typical output that you can generate by performing the by using the NDVI is, I think I have shown this previously also. Yeah. So here, uh, this is a high resolution image, Iconos 4 meter by 4 meter. So if you see this particular image, if I zoom in, so you can see two different types of vegetation. So the shades are different, and these are two different types of vegetation that is formed. And by pan sharpening, this 4 meter is reduced to 1 meter by 1 meter, and after pan sharpening, the NDVI is computed. So the grayscale image is the pan sharpened image of NAR band, and in the NAR band you can see two different types of reflectances being exhibited by the vegetation. Now we need to isolate. Now we need to classify both of differentiate both these vegetation. So by the spectral signature, we know that each and every material has its own reflectance properties. So when we compute the NDVI, the resultant of the dark shade and the resultant from the light shade should be ideally different. So in this case, if you see the histogram, it will be having a bimodal histogram. Then when you adjust the thresholding in such a way, you will be able to differentiate two vegetation, not very exactly, but you will be able to like separate it out by at least 50% or 60% accurate. You will be able to separate. So when you compare the second and the third image, you can see it is mostly separated. So this is one of the application by how you can make use of the NDVI to classify different types of crops. And there are a lot of images. There are a lot of studies that has been going on. You can search for some journal papers also. Is this clear? Okay. Now we'll go to the next part. So somebody asked me whether NDVI is the only index. There is another index similar to NDVI. So that is soil adjusted vegetation index. So here, why they are doing this is in when you do the when you take the NDVI, your soil will also reflect, and it will have a similar NDVI value, which is a little bit less than your actual vegetation index, which is less than the actual NDVI of your crop. But it will also get mixed up in the regions where you have very less crop cover, and your soil is also visible in the particular image. So let's say if your crop space is more, your soil also will uh, be classified under when you try to separate this out. So in order to make an adjustment, the soil adjusted vegetation index was brought out, and here they are adding a factor in both the numerator and denominator, that is L. And if you refer this literature, you will be able to find a value of zero point 0.5 minimizes the soil brightness, and it eliminates the need for additional calibration for different soil. So by this you will be able to take you'll be able to find out the vegetation more accurately. And this is one of the indices. Like this, there are several indices. And here, this SAVI also ranges from -1 to 1, and positive values indicate higher vegetation cover, and negative values may indicate bare soil. So it is the interpretation is also similar to the uh, NDVI only. So this demo only I showed you just now. So now, once we these are all some of the classification. These are all some of the interpretation methods. Ultimately, what we are going to do is we are going to classify the image into different classes, different set of classes, and we will produce a land use land cover map. This is one of the application, and for that we need to do some analysis. That is the image classification. So here we will extract the thematic information, and we will assign classes to each of the DN values. So urban, forest, water body, these are all the different classes. And we will group this DN values in such a way that they belong to a particular category. So how we are grouping it? All the pixels should have a similar spectral reflectance. So from our study area, we will be grouping all the uh, pixels that are having a similar spectral reflectance into a single class. And here we have two types of classification. One is supervised classification, and another one is unsupervised classification. And in the land cover maps, you need to understand two different terms. So one is land use, and another is land cover. So land cover refers to the type of material that is present on the landscape naturally, and land use is what people do on the land surface. So these are two different terms that are usually confused. By how your land cover and land use can change is so your land use might be intended for some other purpose, but let's say if you have a plot area and you leave it for a very long time, but that plot area is intended to build a building, but then it's not built yet, and there is a lot of vegetation. So your land use is urban, but your land cover that is currently present on the landscape is vegetation. So this is the difference. This intricate difference you just need to remember. And we need to select before classification. We need to select these are all the number of classes that we are going to do the classification for. And how we are going to select, there are different levels. So level 1, level 2, and we have level 3 also. So if you say level 1, it is just urban built up land, and if you go to level 2, we can say whether it is residential or commercial or industrial, and we have n number of level 2 classes. And similarly, agricultural land, range land, and their classes, forest land, and their different subclasses. So first you need to decide what is the level of classification that you are going to do. What is the purpose of the study? If you are going to differentiate different crops, you need to go for level 2 or level 3 classification. And if you just want the land use land cover, level 1 is good enough. And we need to choose the product that we are going to use, the resolution, and we need to perform all the pre-processing techniques. Then we need to do some visual interpretation to identify what are the classes that are present. You can make use of false color composite, or you can make use of the indices which you have used, just to get an idea what are the classes that are present in the landscape. Then next one is the ground truth data collection. This is very very important to determine the accuracy of your classification. So we need to go to the ground. We need to identify physically, like what is the land cover that is present in that particular location. So we need to collect a lot of ground truth data to do the accuracy analysis. Then the spectral signature of the ground elements. By using a in situ spectroradiometer, we need to collect the reflectance from the site. So, and we will assign class for that. So if you go to a agricultural field, you take the spectral signature from the agricultural area, and then you assign the values as agriculture. Similarly, for different classes, you will do that. Then we will come to our satellite image. We will take the spectral signature from the satellite image, and we need to assign by some algorithm. We need to define these are all the classes, and then we will label it. Once we get the information class and the spectral class, we will make use of this both to do the accuracy assessment to determine our accuracy of our classification. So here we have a supervised classification and unsupervised. The primary difference is for supervised classification, you need to have training data set. So that is, it can be your part of your ground truth data itself. Let's say if you are collecting 100 ground truth data points, you can split this 100 points into 70 percentage for training and 30 percentage for testing. So you will make use of 70 points to train your algorithm, and the remaining 30% after classification you can use it for testing your algorithm whether it is accurate enough or not. And in supervised classification, we already know the land cover types. So we will go to the places and we will say these are all the land use classes I want in the final output. So we already know what are the classes. And for this, lot of data is required, and it is a very extensive process, and it needs, but it will give you the accurate outputs. But in unsupervised classification, we don't know what are the classes that are present in the our study area. So we are not familiar with the study area, and you also don't have any means to go and collect your ground truth data. And by doing the unsupervised classification, we will just give the number of classes that you need to produce. So let's say you want 5 classes, and then you run the algorithm, it will produce 5 classes, and it will not say class 1 is urban, class 2 is agriculture, like that. So then we need to do some visual interpretation, and then we need to find out what is the class. And for this, much ground truth data is not required. Only for accuracy assessment, you will need the ground truth data. So in unsupervised classification, there is no training. You will directly run the algorithm and then assign the classes later. In supervised classification, you need a training data, you know the classes, and you will perform the classification. So while doing this kind of analysis, you will it will be inherent in the algorithm. So scenario 1 will be like you are taking the training data for a supervised algorithm. So this is your x-axis is band 1, band 2, band 3, band 4, and your y-axis is your reflectance. and you plotted a spectral signature plot. So first, this is the ideal scenario. So you have plotted two different signatures, and the difference of the spectral difference between these two classes are very high, and you can clearly say that there are two different types of classes, and the chances of overlap are very minimal because you have a sufficient number of bands where the spectral difference is very high. And when you plot the spectral difference, you will also encounter such kind of plots. So here, within one class, the intra-class variability. Within one class, the variability is very high, and between the class, the variability is high again. So if you take this line and this line, the spectral difference between these two lines are very high. So in this case, when you try to classify, it may not be ideal for you to go with level 1 class alone because you have different signature within class B itself and different signature within class A itself. So you may have to go for a level 2 classification when you encounter such kind of spectral signature plot. And the third scenario, so when you encounter such kind of scenario, your spectral signature is between class B and class A, both are mixing. So when you try to classify this, you will have lot of misclassification, and your accuracy of the output will not be to the required extent. So in this case, it is very very difficult to do the classification, and you may have to check whether the training data that you chose is not proper or not, and you should select your training data in such a way that this kind of mixing between the spectral signature is not too much. So let's say that you have taken the training data and you have run the algorithm, then you need to do the accuracy assessment for the classification.
Will you show scenario 2 again? Scenario.
Scenario 2. Okay. So in scenario 2, if you, let's say you are taking some nine points from a study area at a different geographic locations, and you are plotting the spectral signature, and you are getting this kind of graph. So if you see for one particular class, let's say this class is agriculture, not agriculture. Let's say this is a forest and this is a very dense cropland. So when you take points from different geographical location, chances are that in this different geographical location, your vegetation may be different. It may be a different type of forest or different type of a crop. Because of that, within class A, you are getting three distinct spectral signature, and within class B, again you are getting three distinct spectral signature. But when you compare class B and class A together, the difference between the lower, this, let's say band 1, band 2, band 3, and for class A, band 1, band 2, band 3, this difference is very high. And within the class also, within class B, the difference is very high. When you encounter such kind of scenario, level 1 classification might not be appropriate because you will be able to distinguish within forest itself different types, and within agriculture itself different types of crop. So in that you can go to level 2 or a level 3 classification.
So as you were saying, difference is very high. Difference in the sense that
Difference in the sense the spectral difference. I think you in the lectures Euclidean distance one terminology was there, if you remember, and parallelopiped classification, that is another algorithm. You remember that?
yes, yes.
So this by calculating the Euclidean distance or a parallelopipe, and when you compare it with your mean of the data, you will be able to distinguish the difference very clearly, and you will be able to assign different classes. So that is what the spectral difference means.
Okay, so one quick question here. See, the ideal scenario,
Yeah,
uh, which doesn't need the level 2 and further analysis, might be the intra low and then inter high. Is it the ideal scenario?
yeah. In the ideal scenario, intra will be less and inter will be high. So
Yeah,
that is
that
the,
would be ideal.
yeah, between
Oh, that is
classes.
for scenario one.
Yeah, that
Okay.
is scenario one. In scenario two, intra will also be high and inter will also be high, so that you can separate. And in the worst case scenario, you will be not able to separate. So everything will be mixed up like this. So we are doing this to find out the accuracy assessment. So your test areas should be representative of the study area. So you should choose the point such that you will have different from your different geographical locations. You will have n number of points, and you should choose the points in such a way that you are selecting it from a uniform land use land cover. Let's say so. If I explain, so let's say this is a study area, and you have a agriculture here, and you have some vegetation here, similar to cropland. We are just having some vegetation here also. So I'm going to have level 1 land use, and I'm going to classify everything as vegetation itself. I'm not going to separate forest, and I'm not going to separate agriculture separately. So I'm going to bring it under vegetation itself. So when you try to do that, you need to select the points such that your training pixel and the testing pixel is from a uniform land use land cover. So let's say this is a very high, very dense agriculture area, and you have lot of green cover in it. You can choose from here. You can choose your training point from here. And similarly, if you identify some other agriculture field like this, you can choose your testing point also from that place. But mostly you should avoid such kind of a sparse vegetation area, because what will happen is it will get classified as both uh, soil or barren land and agriculture or a vegetation. So you will have lot of mixing happening between your barren land and your vegetation when you try to choose your training points from a very sparse or a very less dense vegetation area. So your testing point should be such that it's from a uniform land use land cover. And obviously your testing point and the training point should be totally different. And the source of reference data, this is your ground truth data. It can be from a aerial photo. You can have some high resolution imagery uh, that was captured, and you can try to visually interpret the different uh, reference data for your accuracy assessment. Then from existing maps, let's say if you are going to if you don't have the ground truth data and you want to classify land use land cover for the year 2015, what you can do is you can make use of the Google Earth image. It is not the ideal way, but when you don't have data, this is the final possible way. Go to 2015, and you can go to your study area. Then you can choose what are the pixels during the same date or at least the same month. So that is from the existing maps, or if you have collected some data in forms of GPS points, you can use that. Or if there is any previously available map, let's say cadastral maps, these are some of the data sets that would be available for some study area. You can make GIS data of that, and then you can use that also for your accuracy assessment. And for testing the data, so we can calculate what is the minimum number of points. That is minimum number of points that is at least required to test your classification. So for that, Fitzpatrick Lynn sample size. So this is one study which was made, and from this minimum number of points uh, that is required for testing can be found. So here P is the, so this is P, this is not Q, this is P. P is the expected percentage accuracy of the entire map, and Q is 100 minus P, and E is the allowable error which is user defined, and Z is the standard normal deviate for a 95% confidence level. So if you desire that your map must be 85 percentage accurate, so you know what is P, then you will be able to find Q, and allowable error is only 5%. Then you can calculate the number of points, minimum number of points that is required. So can you quickly calculate for 85% accuracy and 5% allowable error, what is the number of points required? So is someone calculating?
Yeah.
So what is the number of points? So when you calculate it, it's coming approximately 195 point something. So for each class that you define, you need to have at least 195 points or 196 points minimum to get the desired accuracy of 85 percentage. So you can see how extensive and how extensively you need to have the ground truth data, and the number of training points that would be required will be much higher than your number of points that is needed for testing. So that is the difficulty with the
Jared, in case of
supervise.
Jared,
In
what is
case of,
Jared exactly? Jared,
yes,
what is Jared exactly in this problem? Jared.
Z is the, for 95% confidence interval, what is your standard normal deviate. So this can be taken from your this tables, standard normal tables.
So here we can directly put that value 1.96.
Yeah, 1.96 only. Yeah.
The expected accuracy here in the problem is 85%, but
Yeah,
the value
expected.
given.
Yeah, 85 percentage. If we want 85% accuracy with the
Yeah,
allowable,
but the standard and normal deviate for the given is for 95%, right?
yeah, that is 95%.
So then here the Z value in the problem will be less than 2.
Yeah, actually, it is approximated to 2 here, but the actual value is 1.96.
So
Okay. No,
that
what I
means
mean is, see,
1.96 square, Z is 1.96, and P is
85,
0.95. P
0.85,
is
0.85.
0.85,
Yes.
and Q is 0.95.
Yeah. So this is
And it is
1.96.
0.05.
Yeah. So 1.96 square into 0.85 into 0.15 divided by 0.05 square. So when you do this, approximately 195 or 196, and if you substitute 2, I think it will come to around 204 or 205 points.
It's 204 for 2.
Yeah. So these are the minimum number of points that is necessary for testing your data set for one class. So if you have 5 class, you need to have 5 into 196 points. That many points you should have. So this is with respect to the number of points that is
That
required.
Z value will be given in the problem.
Yeah, it
If
should
we
be
get,
given. If it is not given, you can refer the tables.
then it should be provided. I think that
Yeah,
Excel
that
should
should
be
be
provided.
provided. Yeah. And finally, what we are going to do is we are going to calculate the different accuracy. So when doing the classification, you might have omission error or a commission error, which means exclusion or inclusion. So represents omission error represents the pixel that belong to the actual class, but are classified into some other class. So if you are saying currently looking for urban, that is a urban pixel, but it has been classified as barren or maybe fallow. So that is the exclusion error. Inclusion means it belongs to some other class, but they are classified into the current class. It may be barren, but it is classified as urban. So this is the mixing of pixels, and we will calculate the overall accuracy. So overall accuracy is the total number of pixels that are correctly classified to the total number of reference pixels, and its accuracy depends on the number and the quality of the training data set. So we will see how to calculate. Then next is the user accuracy. So from the perspective of a user of the classified map, how accurate the classification is. So that we can also put in another other words. So from a given class, how many pixels on the map are actually what they are indicating. So if you take some 10 pixels, it is supposed to be agriculture, and we are going to see whether it is actually agriculture or not. Then next is the producer accuracy. So from the producer, from the perspective of the producer, how accurate the classification is. So that is for the given class, how many pixels are labeled correctly. So if we take group of 10 pixels, how many pixels are agriculture. So there is just a minor difference. You can understand either user accuracy or producer accuracy, and the opposite of that will be the other one. So if you study everything, then you will get confused. You can remember one, and the opposite of the one which you remember is the other accuracy. So we will see there is one more final statistic, that is the kappa statistic. It reflects the difference between actual agreement and agreement expected by choice. So the meaning of this sentence is whether a particular class got actually classified into the agriculture, or is it just by choice. That is because just because of the algorithm it got classified, or whether it is actually classified. So not just by luck, you can say. To put in simple terms, it is just not by luck, but it is actually classified that it is agriculture. So that is the simplest meaning. And kappa of 0.85 means, so 85% it is classified by agreement than by chance alone. So it is not just by luck, it is actually classifying 85% accurately. So, and the formula for kappa statistic is this is already given in your video lectures. So it's the same formula. So n is the total number of pixels used for accuracy assessment, and a is the total number of correctly classified pixels. Then b is the sum of product of total number of correctly classified pixel into total number of ground truth pixel for each class. This we will see how to calculate. So this is one of the classification which I made during the course, and this is the confusion matrix. So confusion matrix. So on the left hand side you have the classes. So this is a level 1 classification. So and on the right and on the column wise you have the reference pixels. So if your class is urban, and if you look at urban, so out of out of 48 reference pixels, 43 got classified as urban, then one got classified as agriculture, one as fallow, three as barren, and so on. So like this you can interpret. And if you say urban and agriculture, how many number of reference pixel got classified, reference pixel of agriculture got classified as urban? So you can say that one pixel of agriculture got classified as urban, and one pixel of fallow got classified as urban, then 3 pixel of barren got classified as urban. So there are total 46 points for urban. Sorry, not 48. There are only 46 points. These are the reference points. So this is the confusion matrix. Now we need to calculate what is the different accuracy: overall accuracy, user accuracy, producer accuracy, and kappa statistics. So I will just switch over to the other slide. Okay. So the first accuracy is the overall accuracy. So to calculate the overall accuracy, what we need to do is we need to identify the off diagonal elements. So the main diagonal elements. So if you have a confusion matrix, so you need to identify the diagonal elements and then make a sum of it. sum of your main diagonal divided by total number of reference pixels. So this is the formula for overall accuracy, and similarly for user accuracy, so your user accuracy is number of correctly identified pixels divided by number of pixels that got classified into a particular class. Then producer accuracy. So your producer accuracy is number of correctly identified reference points of a given class divided by total number that is actually present in the particular reference class. So let me just flash the problem over there, then we'll calculate. So this particular output you will get as a result of your classification in QGIS. I will try to show a small classification demo maybe in the next session, so that you can get all the results in just a single file itself. So in this, we need to find out what is the total number of pixels. First thing is we are going to calculate our overall accuracy. So if you see the main diagonal elements, so that is highlighted already. We need to make the summation of that. So overall accuracy so that will be 43 plus 38 plus 18 plus 45 plus 38 plus 47. So that comes to around 229 divided by total number of pixel is here. So that is 264. When I divide 229 by 264, so it is around 0.86. So which means it is classification is 86% accurate. So I am just working out on the other screen. I will show that once we complete the calculation. So next one is the user accuracy. So for each class that you have here, you will have the user accuracy. So if I calculate the user accuracy for Baron, so I will take how many number of pixel that is actually classified, that is correctly classified as Baron, to the total number of Baron pixels. So that will be 38 by 48 into 100%. So that will give you 79%. So similarly, we can calculate for. So if you see water body, it is almost 99%. So only one pixel got misclassified. So it's almost 99%. And if you see forest, so that is if I say forest, so that is 45 by 47 into 100%. So that will be around so 95.7% forest is accurate. So similarly, you can calculate it for all the classes. So coming to producer accuracy. So from the perspective of a producer, we are going to see how accurate is the map. So I will do the same thing for same classes so that you can understand. So number of correctly classified pixel divided by the total number of pixels that is classified as Baron. So these are the total number of pixels classified as Baron. So that will be 38 by 48 into 38 by 49 into 100%. So that comes to around 77.5%. And forest, so that's going to be 45 by 47. So it's going to be same as your user accuracy. So that is 95.7%. So finally, we need to calculate the kappa statistic. So total number of so your kappa statistic formula is n into a minus b divided by n square minus b. So that will be 264 into summation of your diagonals. So that will be 229 minus sum of product of row and column. So that is going to be 48 into 46. So your B value is a product of this value multiplied with this value, and you need to do it for all the classes and then sum it up. 44 into 45 plus 29 into 30 plus 47 into 47 plus 48 into 49 plus 48 into 40 divided by total number of pixels the whole square minus again your B value. Okay. Uh, I have taken all the values that I need. Now I'll share my other screen. So overall accuracy is total number of pixel by 264. Uh, I hope that is clear. Then user accuracy for barren is 79%. Then forest is 95.7%. Then producer accuracy for barren is 77.5%. Then forest is 95.7%. Then finally kappa statistic. So this is the value for B. Summation of the columns and summation of the rows. For each class we are multiplying. So if I calculate the kappa statistic, 48. So the value of B is around 11,971. 264 into 229. So if I calculate this, so your kappa coefficient is 80.8399. So we can say that 83.4% of the classification is actually by choice, and it is not just by chance. So ideally your kappa coefficient should be closer to 1. So higher the coefficient, more accurate is your classification. So is there any doubt in the calculation part of the accuracies? Please discuss question number 4 and 8 of the assignment. Okay, I have not yet seen the assignment 4. Maybe I'll try to add it along with the PPT. Anyone has a doubt in the classification accuracy?
Hello,
Yeah, hello.
sir. I have got doubt regarding.
Any other doubt with respect to digital image classification?
Yeah, well, just a couple of questions. See, this NDWI, right?
Yeah,
So, when you are explaining, you have taken bands into consideration, which are green and then NIR.
yes.
So, but in the lecture part, right, it was green and SWR. Is it fine?
SWAR. Yeah, SWAR is with respect to the moisture content in the vegetated areas. So
Okay.
if you want to find out, let's say in among the agricultural area, so which place is having irrigated water. So when you want to estimate that kind of, let's say you have a paddy crop and paddy will be like flooded with water for irrigation. So when you want to estimate that kind of areas, you can use that particular formula. So that will be NIR and SWIR combination. But what I have said is to estimate or find out big water bodies like lakes, ponds,
Okay.
rivers, and other surface water bodies. It is
Okay.
not with
And
respect to vegetation.
so these, right, which for say for these kind of what is analysis, this kind of band should be taken. Is it something derivation we have, or like it's just testing, going on testing, and then we have just found it out?
So how people have done is it's all from your spectral signature only. So in spectral signature, each material has a certain absorption bands and reflectance bands. So if you take for water, your absorption band is NIR and your reflectance band is blue. So low and high.
Okay.
So
Okay.
by exploiting these two properties, they have found out several indices for image interpretation.
Okay.
So it's all with respect to your signature only.
Signature. Okay. And the next one is, see, of course, we have studied digital image processing, and then now we are also learning about this image classification, right? So
Yeah,
probably I think both the things ultimately what we need to do is find out the what you say on ground reality, right?
yeah, yeah.
So what is the difference? Is it something digital image is first level of analysis, and then improvised version is image classification?
So image is like just a photograph. You are asking difference between image interpretation and
Yeah, image
classification.
classification and then digital image processing.
Okay. So processing is where you try to understand the features on the satellite data which you got. And you can also one of the thing is you can make use of NDVI, which is a digital image interpretation technique or image processing technique. Just by using that, you can try to find out the different types of crop. So that is one part of the analysis. So similar to that, you have several applications in the processing part. In classification, we are going to bring out a final product. Let's say a land use class for four different decades. And by using this product, you can make use of these products to for further analysis. Let's say you can build a land use change model. You can predict what will be the land use change in the future by just making use of the four land use class. You can use some uh, artificial neural network or sleuth
Okay,
model
got it.
or land use change models. You can do it for the future, and then you can make use of that in your water hydrological models for
So this is
uh,
prediction all about for
yeah.
the image
So
classification.
yeah, you are going to bring a final product which can be applied. And there are other applications also. You can also determine maybe I think in microwave remote sensing, one of the application is identification of the oil spill. So you can make use of that, and you will be able to find out where the oil spill is happening and what is the trajectory that is going to move. You can do all kind of analysis. That is again a
Right.
image classification,
Yeah.
and it also has image processing plus classification. Both methods interlink together.
Oh, yeah, got it.
Yeah.
Hello.
Yes.
Sir, I want to ask one question regarding basic fundamental question, that is LU, land use, land cover.
Yeah.
How to go to find out the areas under different classification? Maybe agriculture, maybe forest, maybe
So
barren, maybe water body.
how to find out?
Calculate, find out area.
Okay. So that is part of the classification algorithms. So what you will, I will briefly explain.
Hmm.
Uh, Let me go to the screen. Yeah. So I will just describe one method, how an algorithm classifies the
Sir, before that, is it possible to extract the area from my imagery?
to get the area for to get the imagery for your
Any,
area.
any class.
Uh, we won't be doing like that. No, you are asking for ground truth data.
Yeah, yeah.
Uh, that should be collected from the PWD office or the engineering division for the state you are living in. So we won't have access to all the datas.
Okay.
Or the one thing what you can do is you can go to Google Earth, then you can try to pick the points. So you can make use of the Google Earth software.
Sure.
So in that you will have a history of timeline. You can go back in time and then see what land use class is present. So from that also you can collect the points. So coming to how algorithm classifies a particular image, so I'll just describe for Parallelopiped. So let's say you have only two bands, band one and band two, and you
Okay.
have made the feature space plot. Now, after determining from the feature space plot, let's say you have identified some clusters. So, so let me put this way. So let's say you have five classes, and after identifying the classes, calculate the mean. So what you will now we have, let's say, okay, now I'll come to the diagram. So you have some identified some clusters, distinct
Okay.
parts. Then you have calculated the mean of that each cluster. So mean by the sense I mean mean for band 4, so class 1, class 2, so on up to class 5. Mean for band 4, class 1, mean for band 4, class 2, so on up to mean for band 4, class 5. Similarly, band 5, class 1, band 5, class 2, so on up to band 5, class 5. So you have calculated this, and you need to identify the points. So these are your coordinates. So you need to find out these points.
Okay.
And then I'm going to plot. I'm going to virtually locate it. So let's say this is for class 5, 4, 3, 1 and 2. Now what uh, we can specify in parallelopiped algorithm is, with respect to mean, take plus minus 1 sigma or 2 sigma and envelop the central coordinate. So by this what I mean is, from this point I will go plus 1 sigma minus 1 sigma in all the directions. Okay. Similarly for class 3, class 5, so this is for only 2 bands. Suppose if you have a third band in the other direction like this, so you will have a complete parallelogram. So you will have some cuboid kind of. Now once you do this, whatever is the set of pixels that are plotted within this particular cuboid will be assigned a class of that particular number. Okay. Whatever is the pixels that are outside this box will be unclassified.
Okay.
So this is one method. Second method is minimum distance to means. In that what you will do is, so I will explain that in the same diagram with a different color. You just need to calculate up to this point, mean of band 4, band 5. Then what you will do is, let's say I am taking one pixel which is here, and I will calculate the distance between all of the points like this. So I will calculate the distance between the pixel P1 to the mean of the pixel of class 5, then class 4, class 3, class 2 and class 1. And I will find out what is the minimum distance. Let's say by visually I can say that this point is near to class 4. So that pixel P1 will be assigned class 4. So similarly, all the pixels will be, each pixel will be computed, minimum distance will be computed, and then it will be assigned to all the classes. But in this case, you will not have unclassified pixels, but lot of mixing will happen, mixing between the pixels, which will reduce your accuracy of the classification. So these are some of the algorithms by which you can classify. And usually, method we will use is maximum likelihood and maximum likelihood. That is the method which we will use. That is based on the probability. This is part of supervised classification. In unsupervised, it is k-means clustering and ISO data method. So I will
Thank you,
try
sir.
to demonstrate if possible, because it is a lengthy process. I will try how I can fit in the within 2 hours. Uh,
Uh, just a quick clarification. See, for the image analysis and then this one, right? We are of course using classification as part of this supervised or unsupervised. But is there any such like use case where we also apply regression?
Regression, yeah, if you have a highly correlated data, from the feature space plot today I showed you, there was a linear correlation. So in that case,
Yeah.
what you can do is you can make a regression line, and you will be able to explain the properties of two bands with a equation. That is what you will get.
So it would be almost between regression happens only between two bands, like
Yeah,
comparison,
yeah.
one-to-one
Only if
comparison.
there is a correlation, very high correlation is there, you will be able to do it. If it is non-linear, you will not be able to determine.
Yeah.
Okay. If there is no further questions, I'll stop.